the flow of current in the opposite direction. Now, the PN junction diode is a two-terminal device. All right, one terminal is called the anode, the other is called the cathode. So there are two ways by which we can apply external voltage. So in one way, we connect the positive terminal of the battery or the voltage supply to the P side or the the anode side, and the negative terminal of the battery to the N side or the cathode side. If we do that, then we say we are forward biasing the PN junction. And in this case, a large current can flow. Now, the other way of applying an external voltage is to connect the negative terminal of the battery to the P region or the anode terminal, and the positive terminal of the battery to the N region or the cathode terminal. If we connect the external voltage in this way, we are reverse biasing the PN junction. And in this case, only a very small current flows through the PN junction. All right, so let's try to understand why. Now, before doing that, let me just recap what we have learned so far about a PN junction under thermal equilibrium. So what you see here is the Venn diagram of a PN junction under thermal equilibrium. The Fermi level is a single horizontal line throughout the entire junction without any gradient. The gradient is 0. There is a built-in electric field that exists at the junction due to the formation of the space charge region. And the built-in electric field is there to block the diffusion of the majority carriers across the junction, such that the drift current that arises from the built-in electric field exactly cancels the diffusion current, giving a net 0 current flow across the junction at thermal equilibrium. All right, so this is what we have understood so far. Now, let's see what happens when we apply external voltage across the PN junction. So let's look at the forward bias case. All right, so as mentioned just now, during forward biasing of the PN junction, the positive terminal of the battery is connected to the P region and the negative to the N region. And we define the voltage applied in this case as a positive voltage here, right? So VA denotes the applied voltage is positive in this case. Now, due to the applied voltage, there is an applied electric field shown by this arrow here, and the applied electric field points from the positive terminal of the battery to the negative terminal of the battery. So it points from left to right in this drawing, okay? Now, remember the direction of the built-in electric field. The built-in electric field always points from the N side to the P side. So for this drawing itself, the built-in electric field points from right to left. Now, as you can see, the two electric fields are in different direction. They are in opposite direction, and therefore they tend to cancel each other. All right. Now, therefore, at this point, it is very important for you to understand that under forward biasing of the PN junction, the junction electric field will be weakened. In other words, it will be smaller than the built-in electric field. All right, because the applied electric field opposes the built-in field, and the net junction electric field is smaller than the built-in electric field. Okay, so since there is now a smaller junction electric field under forward biasing, the width of the depletion region will decrease because now only a smaller amount of space charge is needed to support the smaller junction electric field. So this decrease in the width of the space charged region is shown here. All right, now the dashed line here shows you the original edge of the space charged region under thermal equilibrium. So the new edge of the space charged region under forward biasing has shifted towards the left, or in other words, Xn now is smaller than Xn naught. Remember, the origin is at the metallurgical junction. All right, so similarly, Xp is now smaller than Xp naught. And the reduction in the width of the space charge region is simply because now we need only a lesser amount of space charge to support the smaller junction electric field under forward bias. Now, remember the purpose of the built-in field. Right, a few moments ago, I mentioned the built-in field is there to block the diffusion of the majority carriers across the junction. Now, under forward biasing, the applied field opposes the built-in field and weakens it. As a result of that, majority carriers can now easily cross or diffuse over the junction. As you know, majority carriers have a very high concentration, and therefore the diffusion of majority carriers across the junction can lead to a large current flow under forward bias. Okay, so what I've mentioned just now have all been summarized here. Okay, so the net electric field under forward bias is smaller than the built-in electric field. There's a slight difference in the notation here. This symbol here denotes the built-in electric field or the electric field at the junction under thermal equilibrium. Okay, this is the applied electric field. And because the net electric field is now lower than the built-in electric field, the space charge width decreases. Okay, now the reason behind this is because I think it's easy to understand that the strength of the electric field is determined by the amount of positive and negative space charge. Right, so since the junction electric field is now weakened, it's now smaller than the built-in electric field, so the amount of space charge also decreases correspondingly. Okay, all right. You can evaluate the maximum electric field, which still occurs at the metallurgical junction, using the same expression as before, except that now Xp replaces Xp naught and Xn replaces Xn naught. Okay. And for an abrupt, uniformly doped junction, the electric field is still a linear function of distance across the space charge region. This does not change. Okay. The next question would be to understand how we draw the energy band diagram under forward bias. Okay. But before that, just a comment. All right, since the electric field is now smaller than the thermal equilibrium case, the total area under the electric field distribution plot is also smaller. All right, and as you know, the area under the electric field plot is actually equal to the voltage across the junction. So the junction potential is also smaller under forward bias. All right, and we can evaluate the junction potential simply as the difference between the built-in potential and the applied potential. Okay, so under forward bias, the energy band diagram has to be modified, since now there is a change in the electric field at the junction as well as a change in the junction voltage. Okay, so the next discussion will be how we can draw the band diagram under forward bias condition. So let me bring you to the next slide. So how do I draw the energy band diagram? Now notice that under forward bias, the two Fermi levels are no longer aligned. They are separated and the amount of separation is equal to the Q, which is electronic charge, times the applied voltage VA. So QVA has a unit of electron volts, well, essentially, okay? Now, why the Fermi level on the P side is now lower than the Fermi level on the N side under forward bias? Now, you can understand this in this way. If you recall what I told you about the energy band diagram last week, we can treat it as an inverted potential diagram. So in other words, the vertical axis, which is the potential energy axis, can be converted into a potential axis. Moving downwards indicates that we are moving towards more positive potential, right? Moving upwards, we are moving towards more negative potential, right? So since under forward bias condition, the P side is applied a positive potential with respect to the N side. And as a result of that, the band diagram on the P side is shifted downwards relative to the band diagram on the N side. And how much does it shift downwards? It shifts by an amount equal to QVA, which is essentially the applied voltage given in electron volts. Okay, so this is the band diagram under forward bias condition. Now, because the P side, the energy band diagram has shifted downwards relative to the N side, this will give a smaller junction potential as well as a smaller junction electric field, as shown by the smaller gradient in the energy band diagram compared to the thermal equilibrium case. All right, now if you go back and check the band diagram under thermal equilibrium case, the two Fermi levels are aligned and you have the built-in potential here. The slope here actually gives an indication of the strength of the electric field across the junction. If you recall, in part 1, you have come across this equation, right, where electric field can be related to the gradient in the energy band diagram, okay? So under forward bias condition, this gradient in the electric field is smaller, right, reflecting a smaller junction electric field. Okay, so that's how we draw the energy band diagram of a PN junction under forward bias condition. Now, since the junction potential now is smaller than the built-in case or the thermal equilibrium case, majority carriers, all right, on both sides of the junction can now diffuse across the junction, giving a large flow of current. Okay. Okay, so I hope you are fine up to this point, right? Now, if you have any question, it is okay that you interrupt me to ask the question. You don't have to wait until the break, all right? Because the break is only 10 minutes sometimes, and it may not be enough to answer all the questions, okay? All right, so that is forward bias. Okay, so now this slide summarizes what I have just explained. So because the potential barrier or the junction potential is now reduced under forward bias, more electrons are now able to diffuse from N to P, and similarly more holes can diffuse from P to N. So a net diffusion of charges across the PN junction takes place. To describe this situation, we say that there is an injection of carriers across the PN junction. All right, so we always say that under forward bias, carrier injection occurs across the PN junction. All right, now since the carriers that are injected across the junction are majority carriers and they are very high in concentration, right, the diode conducts a large current under forward bias, okay? Now, so let's see what happens under reverse bias. Now, in reverse bias, we connect the negative terminal of the battery to the P side and the positive terminal to the N side. Now, if we keep to the same notation as shown here, VA is a negative value under reverse bias condition. All right. Now, due to the applied external voltage, there is an applied electric field. Now, under reverse bias, essentially the N region is made more positive with respect to the P. So the applied electric field points from right to left, which is in the same direction as the built-in electric field. So the two electric field reinforce to give an even larger electric field at the junction. Now this electric field, this net electric field at the junction is larger than the built-in electric field. Okay, because the two electric field add up together. Now, recall what is the purpose of the built-in electric field? It serves to block the diffusion of the majority carriers under thermal equilibrium. And now under reverse bias condition, the junction electric field is even higher than the built-in electric field or the thermal equilibrium case. So obviously, majority carriers cannot move across the junction under reverse bias. All right, so because of this, the diode cannot conduct a large current under reverse bias condition. However, there is still a very small current that can flow across the junction, and I'll come to this shortly. Now, since the net junction electric field is now larger than the thermal equilibrium case, or the built-in electric field, we need more space charge to support this larger electric field, and therefore the width of the space charge region is increased under reverse bias condition. All right, so the original H at thermal equilibrium is shown by the dashed line. The new H of the space charge region on the N side is shown by the solid line here. So Xn becomes larger than Xn naught, and likewise Xp now is larger than Xp naught. Okay. All right, so I've explained that just now. So what I've explained is summarized here. Okay, so the since the electric field across the junction under reverse bias condition is increased, so the total area under the electric field plot is now also larger than that under thermal equilibrium, and this is reflective of the larger junction potential across the PN junction. All right, because under reverse bias condition, the built-in voltage and the applied voltage add up together, right, to give you a larger junction voltage. Now remember, VA by this definition is a negative quantity. All right, so the VJ is actually larger than VBI under reverse bias condition. All right, so the next question will be to answer is, next question that we want to answer is how to draw the energy band diagram under reverse bias condition. All right, if you have understood what I've said earlier about the energy band diagram being a inverted potential diagram, you would have guessed how it can be done under reverse bias condition. So let me show you the energy band diagram first. All right. So since under reverse bias condition, the P side is made more negative with respect to the N side, the band diagram on the P side will now shift upwards relative to the band diagram on the N side by amount equal to QVA, magnitude. All right, remember VA is a negative quantity under reverse bias. Okay, so this relative shift in the band diagram of the P and N side, all right, results in a larger junction potential and a steeper gradient of the energy band diagram, reflecting a larger electric field across the junction. Okay. Now, due to the larger potential barrier and the larger junction electric field, majority carriers on both sides of the junction cannot cross the junction anymore. Okay, and in fact, they cannot do so under thermal equilibrium. Their movement is cancelled out by the opposite drift caused by the built-in field. So in this case, the total electric field is even higher than the built-in field. So that basically rules out the movement of majority carriers across the junction. However, if you examine the direction of the electric field under reverse bias condition, you can easily realize that this direction actually favors the movement of minority carriers on both sides of the junction, across the junction. All right. Now, if you consider the P region, what are the minority carriers? They are the electrons. All right. So the electrons can actually easily drift across the junction under reverse bias. Okay. Now, since electrons are minority carriers, they are very small in quantity, right? And therefore, the current due to the drift of the electrons, right, is very small. Similarly, right, holes, which are the minority carriers in the N side, can easily drift across the junction under reverse bias. All right, being minority carriers, the resultant flow of current is also very small. Okay, so this explains why the diode can only conduct a very small current under reverse bias condition. Okay, so this slide simply summarizes how the band diagram can be modified under reverse bias condition. And this slide simply summarizes why the PN junction can only conduct a very small current under reverse bias condition. Okay, because the charges that can move across the junction under reverse bias are the minority carriers on both sides of the junction. Okay, now I will KIV the second point a bit later. All right, it will become clearer if I explain it a bit later than now. Okay, all right. Now to describe the movement of charges across the PN junction under reverse bias condition. All right, we give it a name. We say that minority carriers are extracted across the junction under reverse bias condition, or under reverse bias condition, there is minority carrier extraction across the junction. All right, so this is a name that people commonly use to describe what happened to the charge movement across the PN junction under reverse bias condition. Minority carrier extraction. Have it on the next slide, if I'm not mistaken. Perhaps not. I want to add it in. Is it here? Okay, I think the word minority carrier extraction might be missing, so you might want to add it in here. Okay. All right. Okay. So now we understand, right, conceptually why the PN junction blocks current flow in one direction, whereas it allows a very large current to flow in another direction, right, in the forward bias direction. Okay. All right. It is all because of the built-in electric field and how it interacts with the applied electric field. All right, and as a result of this interaction, the net electric field can either be smaller than the built-in field or larger than the built-in field. All right, so it is these consequences that determine the rectifying behavior of the PN junction. Right. So the next point I want to make is on the equations that we derived previously under thermal equilibrium condition. Now, since we now understand that the junction electrostatics, right, are modified under external voltage biasing. So obviously we cannot use the same equations anymore. And fortunately, we do not have to rederive all the equation. We just need to make some straightforward modifications. All right. Now, in modifying some of the equation, you need to remember. All right, you need to remember what happened to the junction potential under forward and reverse bias. Okay, and under forward bias, the built-in potential and the applied potential compensate each other, giving you a net potential that is smaller than VBI, right? But also under reverse bias, they add up to give you a potential larger than VBI. Okay, so in equations that you see VBI term, all right, you just need to replace the VBI term with VBI minus VA. And you can continue to use some of the previously derived equation. So just to give you some examples, this is how we can modify some of the equations. Like for example, we earlier derived the width of the space charge region, xn naught, right? The width of the space charge region, xn naught in the n region under thermal equilibrium. Now, under external voltage bias, we no longer write xn naught, we write xn. I will come to this point shortly, why we drop the 0 at the subscript. Okay, so we write xn, and then in the equation itself, all we need to do is just to modify or to replace VBI with VBI minus VA. Okay, all right, the same goes for XP and the total depletion with W. Now, notice that the 0 in the subscript has been dropped, and there's a reason to it, because when an external voltage is applied to the PN junction, it goes into non-equilibrium. All right, so therefore we drop the 0 in the subscript. Now, how to understand that? Now, remember what you know about non-equilibrium. All right, under non-equilibrium, what it simply means is that there is either an excess or a deficit of carriers in the semiconductor. All right, as a result of an external excitation. And under forward bias condition, this is precisely the situation that we have. Remember what I said earlier about the carrier injection due to the weakened junction potential or the junction electric field? Majority carriers are injected from one side into the opposite side. For example, electrons are injected from the N side into the P side. Now, as a result of this electron injection from N to P, all right, we have a higher concentration of electrons inside the P region. In other words, we have excess minority carriers or excess electrons inside the P region. Similarly, due to the injection of holes from the P into the N, we have excess holes inside the N region. All right. And as a result of this, the semiconductor or the PN junction goes into non-equilibrium. Okay. Now, what about under reverse bias? Under reverse bias, we have minority carrier extraction across the junction. In other words, minority carriers from the P side, for example, electrons from the P side are pulled over to the N side. All right. So as a result of this extraction, the concentration of minority carriers or electrons in the P side decreases below the thermal equilibrium value. Similarly, the concentration of holes in the N side decreases below the thermal equilibrium value due to holes being extracted to the P side under reverse bias condition. So there is again a change in the carrier concentration, all right, in the two regions, and therefore the PN junction goes into non-equilibrium. Okay, all right, so you need to keep that in mind. All right, so I've shown you how to modify some of the equations, all right, so that you can continue to use those that are derived earlier. Okay, this is another example where I show you the maximum electric field. So when you calculate the maximum electric field, just keep in mind that xp naught is replaced by xp and xn naught is replaced by xn, right? Okay. Okay, so let's do some simple numerical calculation to find out what happens to some of the parameters, like, for example, the width of the space charge region, right, under an external applied voltage. So let's consider a silicon PN junction at T equals to 300 Kelvin with doping concentration of Na 10 to the power 16 per centimeter cube and Nd 10 to the power 15 per centimeter cube. Calculate the width of the space charge region when a reverse bias voltage of 5 volts is applied. And what is the space charge width if the reverse bias is increased to 15 volts? It's a very simple exercise, but the whole idea is just to have a feel of how some of the parameters change under an external voltage. All right, so under an external applied voltage, the depletion width equation has to be modified by replacing the VBI with VBI minus VA. The rest of the terms are unchanged because they are usually constants. Okay, so only the voltage term here is changed. So for a reverse bias of 5 volts, VA is minus 5 volts, okay, based on the way we define VA, right? So in order to calculate W, we need to calculate the built-in potential. And we already did that previously from the earlier chapter. In example 1, we have already calculated VBI to be 0.635. You can counter check on this. And by just substituting in the numbers, you can determine W under reverse bias voltage of 5 volts. So let's compare the two numbers under reverse bias voltage of 5 volts and under thermal equilibrium. Okay, so obviously the depletion width is now increased, and this increase is because a greater amount of space charge is needed to support the larger junction electric field under reverse bias condition. Okay, so how to calculate the space charge width at 15 volts? You can do the same exercise over again, but you should actually realize something. In this equation, you should realize that W is proportional to the square root of VBI minus VA. The rest are constant terms, right? So since you know the WF minus 5 volts or a reverse bias voltage of 5 volts, you can easily determine the new space charge width at a reverse bias voltage of 15 volts, or VA equals to minus 15 volts by direct proportionality in this manner. Okay, so the depletion width doesn't go up 3 times when the reverse bias voltage is increased 3 times because of the square root dependence. Okay, all right, but nonetheless, it becomes wider, all right, because more space charge is needed to support the higher junction electric field. Okay, so let's do a bit more examples. So in the next example, all right, you're asked to consider a silicon PN junction at 300 Kelvin with a p-type doping concentration of Na equals to 10 to the power 18 per centimeter cube. You're asked to determine the n-type doping concentration such that the maximum electric field does not exceed this value 3 times 10 to the power 5 volt per centimeter at a reverse bias voltage of 25 volts. Remember, when a reverse bias voltage is applied, the junction electric field is increased. And in this example, all right, we need to determine a suitable n-type doping concentration such that the net junction electric field is smaller or at most equal to this value, right? Now, recall that the junction the maximum junction electric field occurs at the metallurgical junction, all right, and is given by this expression. Now, where does this come from? Okay, you can derive this by noting that the maximum electric field, all right, is either expressed as this or this, right? It's QNAXP over the permittivity or QNDXN over the permittivity. All right, but XP and XN are themselves given by these two expressions here. Okay, all right, so to obtain this equation shown here on the previous slide, all you need to do is to substitute either Xn or Xp into this expression for the maximum electric field. Okay, and after some simple algebraic manipulation, you should be able to arrive at this equation. Okay, so the problem that we have in this example is that NA is known, ND is unknown, and VA is 25, or rather minus 25 volt because it is reverse bias, right? And we want to ensure that the maximum electric field is less than this value. Now, if you look at the equation, there is another unknown besides ND, and this other unknown is VBI. All right. If you recall, VBI is given as KT over Q natural log NAND over NI square. All right. So VBI becomes an unknown because ND is not known. All right. All right. So two equation, two unknown is a bit difficult to solve. All right. In other words, even if you try to use the equation for VBI into this expression here and into this expression for the maximum electric field here, you cannot easily solve for ND because VBI has a log dependence on ND. Okay, right. So we need to find a way to simplify the problem such that we can solve it analytically. So how do we do that? So that's the next question. Okay. Fortunately, for this given problem itself, the applied voltage VA is minus 25 volts, or the magnitude is 25 volts. And if you may recall, VBI for a silicon PN junction is typically 0.7 volts. And due to the large difference between these two quantities, or in other words, VA is much bigger than VBI, right? VA is minus 25. If you take the magnitude, it's 25 volts. It's much bigger than 0.7 volts. So one way to proceed is to neglect the VBI term here. Okay, is to neglect the VBI term here, and therefore the maximum electric field expression can be simplified into this form. So now we have gotten rid of VBI and we are only left with one unknown, which is NA in this equation. And we require the maximum electric field to be less than or at most equal to 3 times 10 to the power 5 volt per centimeter. And solving the inequality will give this result where ND cannot exceed 1.18 times 10 to the power 16 per centimeter cube. Okay, now this example also gives you a practice on how you can design the PN junction to fulfill certain requirements, right? You can think of this example as a design question where you're asked to design a PN junction where the P-type doping is known, but the N-type doping is not known, right? Such that you need to fulfill this condition here, right? Where the maximum electric field cannot exceed this value under a reverse bias voltage of 25 volts. Now there is a practical relevance to this example, which I will not discuss at this point. Okay, I will defer it till later when we discuss the chapter on the breakdown of the PN junction. Okay, right. Okay, so that's example 2, right? Okay, at this point, I want to move to some supplementary notes I have prepared. Now, I think you do not have this yet, but never mind, because in the usual lectures conducted in the LT, I would sometimes write on the board. So these are some of the things I will write on the board. All right, but of course now being an online lecture, I cannot write on the board easily. So I prepared some notes in advance and I'll go through them. You don't have to worry. If you need a copy, you can get it from the course site. But essentially, since the session is being recorded, all right, you can still view it later on, okay? All right, so at this point, right, we have a conceptual understanding on what happens, right, when an external voltage is applied to a PN junction. So let's recap, all right, and put in perspective the kind of problem that we actually have on hand, all right? After the discussion, you will realize that the problem that we have is none other than a non-equilibrium problem, which you have actually attempted before, all right? So let's recap. Under forward bias, I mentioned that we have carrier injection across the junction. So electrons from the N side are injected into the P side. Notice that this injection happens at one end of the P region. Now, similarly, holes are injected from the P into the N, and the holes are injected at one end of the N region. Now, if you recall what you have learned in the chapter on non-equilibrium, you have seen such examples before where minority carriers are being injected right at one side of a semiconductor. And how do we analyze such a problem? We can analyze this problem by solving the continuity equation, okay? All right. Now, I mentioned earlier that the injection of carriers will put the two semiconductor region into non-equilibrium just now. I already mentioned that. And the injected carriers, if you look at the P side, for example, the injected electrons will diffuse along the quasi-neutral P region. I will KIV the explanation of this term quasi-neutral region till later. Okay, till later. Don't worry about this. But essentially, this is the P region in this example that I'm trying to discuss. So the electrons are diffusing along the P region, and as they diffuse, they will recombine with the majority carriers, which are the holes in the P region. Okay, so such a problem can be solved by solving the continuity equation, right? And we will only consider steady state condition. Okay, so you probably know what the solution is already, because if you can recall what you have learned under the chapter on non-equilibrium, essentially, if you examine the electron concentration profile along the P region, it is an exponentially decaying curve. All right, so similarly for holes, the hole concentration profile along the N region is an exponentially decaying curve. All right, we'll come to that shortly. Okay, so what happened under reverse bias? We have carrier extraction. All right, we have carrier extraction, and as a result of electrons being extracted from the P to the N side, the electron concentration in the P goes below the thermal equilibrium value, and this put the P region into non-equilibrium. A similar explanation applies to the N region. Okay, now, as a result of the electron extraction, for example, this will lead to a non-zero concentration gradient in the electron concentration along the P region. Now imagine electrons are being pulled out of the P region at one side. Obviously, the electron concentration here will decrease, and therefore that will give rise to a non-zero concentration gradient along the P region. So this concentration gradient will drive the diffusion of the electrons from the p region towards the edge of the space charge region for extraction across to the n side. Okay, now this situation is new, right? I think you did not have such an example under the chapter on non-equilibrium. But essentially, it's just the opposite case, right? Earlier on, we have excess carriers. Now we have a deficit of carriers. Okay, so it's very similar to the previous case. Now, the profile of the minority carrier concentration at steady state can similarly be obtained by solving the continuity equation. We will come to this very soon. Okay, all right. Now, notice that later during the discussion, just in case I forget to emphasize this, so I put it down here first. We will solve the continuity equation in the quasi-neutral region. Okay, what is the quasi-neutral region? All right, so let me come back to this diagram. I will borrow this diagram to explain the meaning behind quasi-neutral region. Okay, this one. Okay. Now, in fact, it might be better if I go to this one and try to help you recall what happens under thermal equilibrium. Remember, the space charge region exists at the junction, and outside the space charge region, the semiconductors are neutral. In other words, the P region is neutral, the N region is neutral outside the space charge region. Okay, so this is one point that you need to remember. Now, the second point is that the space charge region, or the so-called depletion region, is depleted of majority carriers. This means that the resistance of the space charge region is much higher than the resistances of the two neutral semiconductor region. Okay, so this is the second point that you need to remember. Now, with that, you can appreciate why people have come up with this term quasi-neutral to describe a PN junction under an external voltage bias. So let's take the forward bias as an example. So under forward biasing, all right, the applied voltage can be assumed to drop almost entirely across the space charge region. Now, this assumption is reasonable because, as what I've just mentioned a few moments ago, the space charge region is the most resistive region among the three. Okay, all right. So as a result of this assumption, we can therefore assume that no voltage is dropped across the neutral P region and the neutral N region. Now, in reality, there is a small fraction of the externally applied forward bias voltage dropping across the P region and dropping across the neutral N region. All right, with this, okay, in mind, and considering the fact that excess carriers are being injected across the junction and the P region now contains excess electrons and the N region contains excess holes. So strictly speaking, the P and N region are not neutral anymore under forward bias condition. Okay, strictly speaking, they are not neutral. But if we neglect the electric field in the P and N, and if we consider low-level injection assumption to be valid, in other words, the concentration of excess electrons in the P region is very small, all right, much smaller than 10% of the whole concentration. Similarly, the concentration of excess electrons in the N region is very small, smaller than 10% of the electron concentration here. Then we can still regard the P and N region as neutral. But since they are strictly not neutral, we call them quasi-neutral regions. Okay, all right, so that is the meaning behind the term quasi-neutral region. Okay. So later during the discussion, we will only solve the continuity equation in a quasi-neutral region because we can neglect the electric field in this region since it is very small. And doing so will simplify the solution process, as you will see later on. Okay, now to be able to completely solve the continuity equation, the boundary conditions need to be known. In other words, we must, if you take, for example, the forward bias case, we must somehow know the electron concentration at the edge of the P region. All right, this is one boundary of the P region. All right, we must know the electron concentration here, and we must also know the electron concentration at the other side of the P region, which is here. Okay, so similarly for the whole concentration, we must be able to know the value here and here. Okay, all right. So this is what I'm going to discuss next. Okay, all right. So we must have a way to determine the change in the minority carrier concentration at the edge of the depletion region. Okay, as well as the other side of the quasi-neutral region where the metal contact is. All right. So I will do that next. Okay, all right. So let's start the discussion. Now, again, this is a recap on thermal equilibrium. So this diagram here, or this plot here, shows you the variation of carrier concentration across the PN junction. Now, what you see here is different from what you have on your slide. I think on your handout, you will see a line joining this level to this level, and likewise this level to this level. Okay, I will explain why I've omitted the lines in this updated slide. So it doesn't matter, you just ignore the two lines. Okay, and the dashed line shows you the carrier concentration profile at the very instant the PN junction was formed. You can neglect those lines as well. Okay, now this is a very simple diagram. Okay, that shows how the hole concentration and electron concentration vary across the PN junction. Now, I have omitted the lines in the space charge region because strictly speaking, we do not know how the hole and concentration, how the hole and electron concentrations vary across the space charge region. We have never attempted to derive any expression for them before. Right, remember in the very beginning when we applied the depletion approximation to solve the Poisson equation, we have in fact neglected the electron and hole concentration in the space charge region. So up to this point, we do not know the exact form of the equation that would describe how the hole concentration varies across the space charge region and the electron concentration varies across the space charge region. So to avoid potential misunderstanding or confusion, I have decided to remove the lines in the space charge region, which are not important anyway, so you do not need to know them, right, at all, okay? All right, because in the past when I included them, some student will ask me, oh, so does that mean that the whole concentration varies linearly across the space charge region and so on and so forth? So their removal is simply to avoid potential misconception. Okay, all right. Now, under forward bias, we have carrier injection. So holes are injected from P to N, so that increases the hole concentration, all right, at the edge of the space charge region on the N side from the thermal equilibrium value to a new value. Okay, so similarly, electrons injection from the N into the P will lead to an increase in the electron concentration at the edge of the space charge region on the p side. All right, so I will show you how we can obtain equations that quantify Pn and Np. Notice that the subscript 0 has also been dropped in these two notations, okay? Because under forward bias, the PN junction is in non-equilibrium. Okay, what is this line that decreases and eventually seems to merge with PN naught? Okay, this line actually describes how the excess hole concentration will vary with distance in the quasi-neutral N region. Okay, later we would have an equation that will describe this line when we solve the continuity equation. Now, what is this green region here? This green region is simply to denote the presence of excess holes, right, inside the quasi-neutral N region under forward bias condition. Similarly here, it denotes the presence of excess electrons in the quasi-neutral P region under forward bias condition. Okay. Now, this is the diagram for reverse bias. Right, for reverse bias, we have carrier extraction across the junction. As a result of electrons being extracted from P to N, the electron concentration at the edge of the space charge region on the P side decreases below the thermal equilibrium value. And this curve here that appears to merge with NP naught shows you how the electron concentration varies with distance, right, in the quasi-neutral P region. Now, the shaded red region here is simply to indicate a deficit of minority carriers under reverse bias condition. Okay, all right. So I think with this probably explained, there shouldn't be any potential misconception arising from these few diagrams. Okay. So now let me proceed to derive an expression for the new minority carrier concentration at the depletion edges under an external applied voltage. Okay. All right. This slide simply summarizes what I've just said. Okay, so under externally applied voltage, the minority carrier concentration at the depletion edges are modified. So we need to learn how to derive them. Okay. I have also mentioned this earlier, right? So the resultant diffusion of these minority carriers in the quasi-neutral regions will determine the amount of current flow, right, in the diode at a given applied voltage. Okay, so now we want to find a way to quantify the change in the minority carrier concentration at the depletion edges, as doing so would help us solve the continuity equation entirely. Okay, so I will start with this equation for VBI. All right, so VBI, earlier on, we have shown that VBI is equals to KT over Q, natural log NAND over NI square. Okay, now, at normal operating temperature, which is typically 300 Kelvin at room temperature, and we can assume that the dopant ions, or the dopant atoms are fully ionized. Okay, and since the doping concentration is usually on the order of 10 to the power 16, which is much higher than the intrinsic carrier concentration, we can approximate the electron concentration in the N region at thermal equilibrium to be ND, and the hole concentration in the P region at thermal equilibrium as NA. Now notice that we have included an additional letter in the subscript here. So the additional letter here, N, denotes the N region of the PN junction. This letter P denotes the P region of the PN junction. Okay, because now we have two differently doped semiconductor regions, so it is important to distinguish which region we are referring to when we are referring to the electron or hole concentration. Now, the respective minority carrier concentration can then be calculated based on the law of mass action. Now, with this understanding, we can therefore replace NA and ND in this expression with the respective majority carrier concentration. Okay? And the minority carrier concentration. So I can express VBI as KT over Q natural log PP0, PP0 over PN0. So how do I get this? Remember NA, right? NA can be replaced with PP0 and Ni square over Nd. So the Nd can be brought below. So we have Ni square over Nd. Ni square over Nd can be replaced by Pn0. Okay, all right. So I can rewrite VBI in an alternative form like this. And also another alternative form like this, okay? So in this expression here, I have replaced ND by NN0 and Ni square over Na by NP0. All right. Now, then I can bring Q over to the left side and as well as KT to the left side and eliminate natural log by raising both sides to an exponential function. All right, so the resultant two expressions are shown here. So Pn0, in other words, the whole concentration in the N region at thermal equilibrium can be related to the whole concentration in the P region at thermal equilibrium by an by an additional factor term here, which is E minus Q VBI over KT. Similarly for the electron concentration, right? NP0 can be expressed as NN0 times E minus Q VBI over KT. Okay, now these two equations are known as the law of the junction, right? You might want to write down this name, law of the junction. Okay, not law of the jungle, but it's law of the junction. All right. This makes a lot of sense. The involvement of VBI here makes a lot of sense in particular. Remember what we said under thermal equilibrium? It is the built-in potential that blocks the diffusion of the majority carriers. All right. And therefore, it is the built-in potential that help us maintain these two levels, right? This being the higher level in the P-type dope region, and this being a much lower level for whole concentration in the N-type dope region. So this difference in the level is being maintained by a built-in potential across the junction, right? Now, imagine the non-physical case where a built-in potential doesn't exist. Then these two levels cannot exist at thermal equilibrium, right? They must become the same level because holes will eventually diffuse until you get the same number of holes throughout the whole PN junction. But that does not exist or is non-physical, okay? All right, because the moment diffusion happens, there's a space charge region form and the built-in voltage will start to form, okay, to counter the diffusion process, okay? All right, so these two equations are important, so keep them in mind, okay? Now, with this established, then we can argue that the same expression can apply under external bias, right? Simply by replacing VBI with VBI minus VA and dropping the 0 in the subscript. This is reasonable because when an external voltage is applied, it simply only modifies the junction potential and the junction electric field. So this modification will therefore lead to different levels in the, or different values now in PN and PP, right? But they can still be related by the net junction potential, okay? All right. Now, at this point, we want to make some assumptions. If the applied bias is moderately low, such that low-level injection condition prevails, in other words, the low-level injection assumption is true, the majority carrier concentration does not change very much from the thermal equilibrium values. All right, and recognizing this, we can therefore replace PP by PP naught and NN by NN naught. Okay, all right, so this is possible if low level injection assumption holds true. Okay, now with this, I can rewrite this equation for the whole concentration at the edge of the space charge region on the N side. All right, in an alternative form like this, I simply breaks up this exponential function into two exponential function terms. Okay, simply by rearranging the exponents. So in the first exponential term, I have e minus q VBI over kt. In the second one, e to the power of q VA over kt. So the two exponents will just add up to give you this expression. All right. Now, if you look at the product of the first two terms, PP naught times E minus Q VBI over KT, and then recall what we know earlier from thermal equilibrium, PP naught E minus Q VBI over KT is none other than Pn naught. In other words, the minority carrier whole concentration at the edge of the space charge region on the N side at thermal equilibrium. Okay, so I can replace the product of the first two terms simply by Pn naught. Now I can do the same for the electron concentration following exactly the same approach actually. All right, so I can relate the electron concentration at the edge of the space charge region on the P side under external applied voltage condition to the thermal equilibrium value multiplied by a factor EQVA over KT. Okay, now Pn naught and NP naught are usually known quantities because doping concentration are usually known quantities. And if the applied voltage is also known, VA is also known, then I will be able to determine the value of the new minority carrier concentration at the edge of the space charge region. So with this, one of the two boundary conditions are determined. Okay, one of the two boundary condition that we try to determine now is known. Okay. All right. Now we can also further express this these two equations in alternative forms. All right, by defining the excess minority carrier concentration. Okay. Excess is simply the change, right? So to the change in the whole concentration at the edge of the space charge region on the N side can be written as the new value under external voltage bias minus the value at thermal equilibrium. All right, so it's a simple algebra, so you can get this expression. So similarly, for the change in the electron concentration at the edge of the space charge region on the P side, can now be expressed like this. Okay. Now, along the way, you can make more assumptions. Like for example, if you consider forward bias, where VA is bigger than 0, and VA usually, for forward bias, it needs to be much bigger than KT over Q. All right. If you recall, KT over Q has a value of only 26 millivolts at room temperature. All right. So obviously, to forward bias a PN junction, the applied voltage has to be much bigger than just 26 millivolts. And because of this, under forward bias, since VA is positive, the exponential term dominates and the 1 can be neglected. And therefore, we have slightly simpler expression for delta PN and delta NP. Now, a similar simplification can be made for reverse bias when VA is negative. So when the magnitude of the VA gets much larger than KT over Q, and remember under reverse bias, VA is a negative quantity, and this will make this exponential term much smaller than 1. Okay, so this exponential term can be neglected under reverse bias, allowing us to approximate the change in the minority carrier concentration as follows. So delta Pn become minus Pn naught and delta Np become minus Np naught. Now, under reverse bias, obviously due to the minority carrier extraction, we have a deficit of minority carriers in the two semiconductor regions. Okay, all right. So this excess, this word excess is enclosed in quotation mark like this, meaning that it does not always mean a positive a quantity. All right, excess could mean negative. All right, well, in other words, under reverse bias is actually a negative quantity, a negative excess, right? Okay, all right. So at this point, I have successfully determined the boundary conditions, all right, at the edge of the space charge region under an external applied voltage. So the next thing we want to do is to solve the continuity equation, all right, to determine how the excess minority carrier concentration vary across the quasi-neutral P and N region. And doing that will eventually lead us to this thing called the ideal diode equation, okay, which simply quantifies the amount of current that flows across the PN junction under a given external voltage bias VA. Okay, so we'll do that after the break. So at this juncture is about 5:20. All right, so we'll take a break and please come back at 5:30. All right, so it's a 10-minute break. Called the ideal diode equation, which quantifies the amount of current flowing across a PN junction diode under a given external voltage bias. So just a quick review of some basic concepts. By now, you should be able to do the followings. If you cannot, then it's time to go back and do some revisions, right? So we just answered some of these questions, like why a PN junction conducts only under forward and not reverse bias. We have drawn.
Prof,
Yeah.
are you sharing your screen? Because we can't really, at least I can't see it.
Oh, I think, yeah. Sorry about that. I think I've forgotten to share the screen. Okay, I think you should be able to see it now. So this is a checklist for you to look at, to double check on your understanding. So make sure you can do all of this by now. Okay. So let me start with the discussion on the ideal diode equation. So the further objective will be to analyze the PN junction, right, quantitatively now, to obtain a mathematical expression that will give us the exact value of the current flow for a given external voltage bias. Now, as mentioned earlier in the earlier discussion, the problem we have on hand is actually one that concerns the transport or diffusion of excess minority carriers along the quasi-neutral P and N region. All right, and such a problem can be solved by solving the continuity equation for the electrons and holes. You have seen some examples on this before in the previous chapter on non-equilibrium, as well as question 4 in tutorial 6. So you can always go back and refer to them if needed. Now, in order to do the analysis analytically, all right, we need to make some assumptions. Some of the assumptions are similar to those that we have made earlier pertaining to the abrupt junction. All right, there are newer assumptions which I will go through them now. The P and N region are uniformly doped all the way to the metallurgical junction. In other words, the PN junction is abrupt. So this was made earlier, all right from the very beginning. Now, the new assumption, right? The second point, the length of the N and P regions are infinitely long compared to the minority carrier diffusion length. Let's see how this assumption can help us simplify the mathematics involved later on. Now, you need to understand this term infinitely long very carefully, right? Infinitely long compared to the minority carrier diffusion length. Now, the minority carrier diffusion length of excess minority carriers is typically in the range of micrometer. All right. So when we say that the length of the quasi-neutral P and N region are much longer than the minority carrier diffusion length, simply means that they are 10 times or more longer than the respective minority carrier diffusion length. So in absolute terms, the length of the quasi-neutral P and N region are not very long either, right? They are not infinitely long. Okay. The applied voltage is sufficiently low such that the low level injection is valid. This is important, okay, for us to simplify the solving of the continuity equation. Now, there is negligible or no voltage drop across the quasi-neutral N and P region. In other words, no electric field in this region. I have mentioned this earlier during the discussion. Okay, so by now you should be able to understand the meaning of the term quasi-neutral N and P region. Okay, now thermal equilibrium prevails at the N contact. So how does this help us? In other words, when you reach the N contact where the PN junction is contacted by metal and connected to the external voltage bias, we assume that all the excess minority carriers would have recombined at that point or at that position. Now, there are no other external sources of excitation except the applied voltage. In other words, we don't shine light, all right? We don't change the temperature. We only apply a voltage. Now, the next two assumptions are important, and please take note of them, and I'll highlight them later on as the discussion goes. The excess carriers do not recombine in the space charge region under forward bias condition. Okay, what does this mean? Now, if you recall, under forward bias, we have carrier injection. So what this assumption simply means is that as the electrons and holes are injected across the space charge region, they do not recombine within the space charge region. Recombination only starts when the carriers enter the quasi-neutral P or N region. All right, I will come to this again later on in more detail. Now, the next assumption pertains to the reverse bias condition. Under reverse bias, we assume no generation of carriers take place in the space charge region. All right, so don't worry if you are not very sure about what this assumption is trying to address. All right, we will come to this in more detail later on. And finally, we only look at steady state condition. All right, so that will help simplify the continuity equation as well. Okay, before I begin solving the continuity equation, all right, just a note on modified x coordinate. Okay, why do we want to do that? Now, as mentioned earlier, in order to simplify the solving of the continuity equation, we will only solve the continuity equation in the respective quasi-neutral region. In other words, we will avoid the space charge region where there is an electric field. All right, in the quasi-neutral N and P regions, we can assume the electric field to be negligibly small and neglect the electric field when solving the continuity equation. So therefore, instead of keeping to the original x coordinate where x equal to 0, the origin is defined to be at the metallurgical junction, right? We redefine the origin, right? In one case, when we solve the continuity equation in the quasi-neutral n region, the origin is taken to be at the edge of the space charge region here. Okay, so originally based on the original definition, this position has a value of xn, right? But now it has been defined as the new origin. Okay, so x is now written as x prime, just to distinguish it from the previous x coordinate. Now, later when we solve the continuity equation in the p region, right, we will use a new x coordinate called x double prime with the origin position at the edge of the space charge region on the p side. Okay, so this is just for convenience, right? It doesn't matter if you want to keep to the original coordinate. If you do that, then you need to always offset the value of x by xn, right? Now the same goes for the reverse bias condition, right? Just take note of the change in the origin. Okay, now let me focus on the quasi-neutral n region. So I will show you step by step how the problem can be solved, right? In the quasi-neutral n region by solving the continuity equation for the holes. Right, so this is the continuity equation for the holes. Some of the terms I think you should already know. Okay, so the term on the left side give us the change in the hole concentration in the n region with respect to time. And this change must be accounted for by certain physical processes, one of which is the current flow, okay, in the semiconductor. So if the current flow is not uniform, then it can cause the hole concentration to change at different locations inside the n region. Now the current flow has two parts, right? One part is drift, the other part is diffusion. Okay, right? So that explains the meaning of the first two terms. Now the third term is GP, which is actually GL previously. So GP actually denotes the electron hole pair generation rate due to the shining of a light. Okay, so since in this case there is no light shining, so GP is actually 0. Okay, later on you will see we will remove GP from the expression. Now the last term is the net recombination rate, right, which is delta Pn over the lifetime of the excess holes, tau P. You need to recall the meaning of this term. Right, now this simplified term only applies under low level injection condition. Without low level injection condition, the expression is more complicated than just this. All right, so that's where low level injection assumption comes into the picture. It helps us simplify this term. Okay. Now, the continuity equation can be further simplified, of course, based on the earlier assumptions that were made. So one of which is that we only consider steady state operation. In other words, the excess hole concentration in the quasi-neutral n region is independent of time. Or in other words, dPn over dt is 0. There are no other sources of excitation. I mentioned this earlier, so GP is 0. No electric field in the quasi-neutral region, so electric field is 0, and that is very helpful because that will get rid of this entire first term here. If electric field is 0, this term is 0, this term is also 0. Okay. We assume uniform doping. Now this is important. If uniform doping applies, then the second order derivative in Pn with respect to x prime can also be written as the second order derivative of delta Pn with respect to x prime. To see this is very easy. Remember the hole concentration under non-equilibrium Pn can be written as Pn naught plus some change, delta Pn. Now, since Pn naught is independent of distance due to uniform doping, then differentiating it will make it go to 0. Okay, so the derivative of Pn can, with respect to x prime, can also be written as the derivative of delta Pn with respect to x prime. Now, with all these assumptions made, the continuity equation can be simplified into this form. And bringing the terms to the right, we can re-express the continuity equation like this, where on the left, you have second order derivative of delta Pn with respect to x prime. On the right, you have delta Pn over Lp squared, where Lp is a new parameter defined as the square root of dp tau p. And later on, in fact, in the earlier chapter on non-equilibrium, you should already know the physical meaning of Lp. All right, this is the whole diffusion length. It describes the average distance an excess hole will diffuse before it recombines. Okay. Now, this is a second order differential equation which has a solution of this form. This is the only solution possible for this second order differential equation. No other form, right? This is the only solution possible. Okay, for those of you who are doing further math, you will probably understand what I'm saying. All right, if this expression satisfies this equation, then this is the only solution for the second order differential equation by the uniqueness theorem. Okay, now there are two constants of integration in this expression, C1 and C2. Why? Because in principle, to solve a second order differential equation, you need to integrate the equation twice. All right, so by integrating it twice, you introduce two constants of integration, C1 and C2, which can be found using the boundary conditions. So this is what I'm going to do next. So how do I find C1 and C2? I make use of the two boundaries. So the first boundary refers to the matter contact n, all right? Or in other words, when x prime tends to infinity, very far away from the edge of the depletion region relative to the minority carrier diffusion length. So since we assume that thermal equilibrium prevails at the end contact, therefore the excess hole concentration must be 0. In other words, all the excess holes have recombined at the end contact. Okay. Now, if we apply this boundary condition, noting that as x prime tends to infinity, the exponential term will tend to 0. What else? This exponential of minus x prime term will tend to 0. Whereas the exponential of x prime term will tend to infinity. Okay. Now, in order for this boundary condition to hold, in other words, in order for this side of the solution to be 0, with E minus x prime over LP becoming 0, and E x prime LP becoming infinity, the only way to make this side of the solution 0 is for C2 to be 0. Okay, so applying this boundary condition allows us to conclude that the constant of integration C2 must be 0. Okay, so with that, we are only left with C1. Now, to determine C1, we can use the other boundary, which is at the edge of the space charge region. Remember earlier, in the earlier chapter, I have derived an expression while quantifying the change in the minority carrier concentration at the edge of the space charge region. And this can be written like this for the delta Pn. Okay. So substituting x prime to be 0 into this expression, C2 is already 0. So you only need to worry about the first term. So with x prime being 0, the exponential term will give you a 1. In other words, C1 is essentially the excess hole concentration at the edge of the depletion region on the quasi-neutral end side of the PN junction. Okay, so C1 is also determined, and with this, the excess hole concentration along the quasi-neutral P region is now completely solved. Essentially, it is an exponentially decaying function with the rate of decay determined by this parameter LP. Right? If LP is large, then the decay is very slow. Right? You can verify this quite easily. If LP is large, this exponential term will tend to be small, right? Making the decay in the excess hole concentration happening more slowly along the length of the quasi-neutral N region. On the other hand, if LP is large, if LP is small, all right, then the decay in the excess hole concentration will be very fast, all right? So LP has meaning, and people give this meaning to LP, the minority carrier diffusion length. So it gives a measure of how far an excess minority carrier can diffuse before it recombines. Okay. Now there's a new term here, long base. Long base diode simply means that the length of the quasi-neutral region is very much longer than the minority carrier diffusion length, 10 times or more. So we call it a long base diode. Okay. Yep, I have explained the meaning of LP, minority carrier diffusion length. Now, if we repeat this exercise on the quasi-neutral P region to determine the excess electron concentration as a function of distance, this will be the solution. So you're encouraged to try out on your own. The steps involved are very similar and the assumptions involved are the same. Okay, so please try to see if you can obtain this on your own. Okay, so at this point, we have partially solved the problem. All right. We now know that how the excess hole and electron concentration vary as a function of distance in the two quasi-neutral regions. However, we do not know anything about the space charge region. Okay, so we need to find a way to complete the whole picture. Now, with the excess minority carrier distribution known, we can then determine the diffusion current due to the excess minority carriers. Okay, all right. Now this diffusion current is coming from the excess minority carriers because these minority carriers are injected at one end of the PN junction. So they diffuse along the length of the quasi-neutral region. All right, and as they diffuse, of course, they recombine with the majority carriers there, which explains why the excess minority carrier concentration decreases with distance. Okay, all right. So what I'm going to do next is to determine the, okay, shown by the solid line. So just be patient. I will show you a diagram later on. Okay. So let's look at the equations first. So to determine the whole diffusion current density in the quasi-neutral N region, we just need to apply this definition. Q dp dpn over dx prime. Remember, dpn over dx prime is the same as d delta pn over dx prime. In other words, you just need to differentiate this with respect to x prime. Okay, and then put it into this expression for the whole diffusion current density in the quasi-neutral N region, and this will be the result that you will obtain. It's a simple exercise, so you should try it out by yourself. Similarly, I can determine the electron diffusion current density in the quasi-neutral P site, okay, based on this definition. Okay, now notice that the electron or hole diffusion current or current density is not a constant, but they also vary exponentially with distance. Okay, now Well, in other words, the diffusion current decreases as a function of distance into the quasi-neutral region. Now, why is that the case? Because as the minority carriers diffuse, they recombine. So as they diffuse, there are fewer and fewer minority carriers, and therefore the diffusion current also gets smaller and smaller into the quasi-neutral region. Okay, right? Yeah, this is the diagram that I was referring to just now. So let me explain step by step some of the lines that you see here. So let's focus on the solid lines. So this is an exponentially decaying function describing the whole diffusion current density in the quasi-neutral N region based on this equation. Okay, right? Now, this is a solid line describing the electron diffusion current density in the quasi-neutral P region based on this equation. Now, at this point, I want to clarify that why I put this value to be higher than this. There is no reason, it is simply arbitrary. Of course, you can have the electron diffusion current at the edge of the space charge region to be higher than the whole diffusion current. Okay, so don't be too concerned about this difference. It's arbitrary. Okay. Now, at this point, this is what I know so far. But the objective that I have here is to determine the total current that flows in the PN junction under forward bias. Okay, all right. So obviously I need to fill in the rest of the picture. Now this is where one of the two red colored assumptions become important. Okay, now remember earlier when we made the assumption, we assume that the excess carriers do not recombine in the space charge region under forward bias. So what that means? That means when the holes are injected from the P to the N, as the holes cross the space charge region, no recombination happens within the space charge region. Similarly, when electrons are injected from the N to the P, when the electrons cross the space charge region, no recombination happens. In other words, recombination of the minority carriers only starts when they enter the opposite quasi-neutral region. For example, when holes get into the quasi-neutral N region, recombination starts, which accounts for the decrease in the diffusion current as a function of distance. Now, with this assumption, and with this value of the whole diffusion current density known at the edge of the space charge region, we can calculate this value using this equation by substituting x prime to be 0, and the rest of the parameters can be known. So Jp at x prime equals to 0 can be calculated. Now, with this value known, and with this assumption of no recombination of electrons and holes across the space charge region, this current must be a constant current across the space charge region. Okay, by a similar argument, the electron diffusion current across the space charge region must be a constant, because as the electrons are injected across the space charge region, they do not recombine. In other words, no electrons are lost, no holes are lost as they get transported across the space charge region. So the current must be constant. Okay, now, since these are the only two currents flowing across the space charge region, the sum of these two currents must equal the total current flowing across the PN junction. Okay, so now with this assumption, the total current is known and can be calculated simply by adding the whole diffusion current density at the edge of the space charge region on the N side with the electron diffusion current density at the edge of the space charge region on the P side. By adding these two values, I determine the total current flow across the PN junction. Now, since under steady state condition, the total current flow must be constant throughout the entire PN junction, shown by this line, this horizontal line here. There must be another missing current component. Since the minority carrier diffusion current is a function of distance, there must be another missing current component that add up with this to give you a constant overall current. Okay. Now, this current in the quasi-neutral N side is none other than the electron drift current, shown by the dotted line here. And on the quasi-neutral P side, this missing current is none other than the hole drift current. Okay. Now, at this point, some of you may ask, why is there a drift current when there is no electric field present in the quasi-neutral P and N? Strictly speaking, there is a very small electric field present in a quasi-neutral P and N. We have neglected the electric field during solving of the continuity equation. We set it to 0, but doesn't mean it is actually 0. There is a very weak, right, electric field within the quasi-neutral region. And this weak electric field is the driving force behind the majority carrier drift current, right? Electron drift current is a majority carrier drift current in the N region. Hole drift current is a majority carrier drift current in the P region. Now, what purpose does this drift current serve? Remember, under forward bias, you have electron injection from N to P. In order to sustain this injection of electrons from N to P, electron must be continuously supplied from the external circuit as a form of drift current. All right, so electron will drift towards the edge of the space charge region, driven by the weak electric field in the quasi-neutral N region, and they get injected to the opposite P side. After entering the opposite P side, they diffuse, right? To give you a electron diffusion current. So there is one role played by the electron drift current. Now there's another role played by the electron drift current because you have holes injecting from the P into the N region, and as the excess holes diffuse along the quasi-neutral N region, these excess holes will recombine with the electrons. So therefore, electrons must be continuously supplied by the external circuit for the recombination with the excess holes. All right, so this is the second role played by the electron drift current. Or in other words, there are two components in the electron drift current. One component is to sustain the injection of electrons to the P side, which is a constant component. The other component is a distance-dependent component, all right? Because electron must be supplied to recombine with the excess holes injected from the P side. Okay, so with this, we complete the whole discussion under forward bias. Now, the same explanation applies to the hole drift current, right? There are two components. One is to sustain the injection of holes to the N side, which is a constant component. And the other component, which is distance dependent, is due to the holes needed to recombine with the electrons. Okay, all right. So with this, the discussion on forward bias is fully complete. And we have also successfully obtained an equation that will quantify the total current flow through a forward bias junction, a PN junction, all right, simply by adding up the respective diffusion current or current density at the edges of the space charge region. Okay, so what I've described are summarized in the next few pages, or rather in the next page, okay? So by adding the two minority carrier diffusion current density at the depletion edges, we get the total current density flow across the diode under forward bias, and this give us the ideal diode equation. Now, why people call it ideal diode? Because of some of the assumptions that we have applied or made in order to arrive at this expression. Okay? So for a given forward bias voltage, VA, you can calculate J. And J naught is a constant term shown by this expression here, which can be predetermined as well. Once the doping concentrations of the P and N regions are known, and the mobilities of electrons and holes are known, and the lifetime of the electrons and holes. Okay? All right. Now, to really complete the discussion, there is still one remaining question to answer. What about reverse bias? Okay, since we have been talking only about forward bias, what about reverse bias? Now, the same equation applies under reverse bias, okay? Because during the solving of the continuity equation, we did not specifically assume whether the PN junction is under forward or reverse bias. Okay, we just say that the PN junction is under non-equilibrium. So this can be forward or reverse bias. So the same expression can be used for reverse bias. And under reverse bias, the minority carrier diffusion current density expression are the same. Okay, all right. So let's see what happens under reverse bias, how to complete the picture, okay? So just a recap on reverse bias. So we have minority carrier extraction, and as a result of the minority carrier extraction, we get a non-zero concentration gradient in the minority carrier concentration, which drives the diffusion of minority carrier from the rest of the quasi-neutral region towards the space charge region for extraction to happen. Okay, and these minority carriers are mostly those found within one diffusion length from the depletion edge. Only these minority carriers can successfully diffuse and get extracted across the space charge region. On average, because minority carriers, they are too far away from the junction, will not be able to make it to the space charge region. Okay. Okay, now I will show you the next slide, which shows you the different current components inside a reverse bias PN junction. And as we discussed, we will cover some of the points here. Okay. Now, before doing that, let me go back to this slide again on reverse bias. All right. So due to the minority carrier extraction, there is a drop in the minority carrier concentration at the depletion edges. So this set up a concentration gradient in the minority carrier concentration profile, driving minority carrier diffusion towards the edge of the space charge region for extraction. Now, because there is a deficit of minority carriers under reverse bias condition, net generation of minority carriers happen within the quasi-neutral region. And it is through this generation that supplies the minority carriers for extraction across the space charge region. Okay, the minority carriers that are thermally generated within the quasi-neutral region. Remember, in a semiconductor at a fixed temperature, thermal generation constantly produces electrons and holes. Okay, now since under reverse bias, there's a deficit of carriers, the generation rate will exceed the recombination rate. Okay, so the recombination of the minority carriers will now be slower than the generation. So with net generation, we supply minority carriers for extraction across the space charge region. All right, so let me go to the diagram for reverse bias. Yep. Okay, here. All right, so under reverse bias, electrons are extracted from the P to the N. All right, and holes are extracted from the N to the P. Now, due to this extraction, we have an electron diffusion current flowing along the quasi-neutral p region. All right. The equation describing this electron diffusion current is the same as earlier here. Okay, all right. So remember, this electron diffusion current exists because of the concentration gradient created by the extraction process. Okay, and what supplies this electron diffusion current is the thermal generation process. Okay, so after being extracted across, all right, this electron will drift, will become the majority carriers in the N region. They will drift along the N region, quasi-neutral N region, giving electron drift current. Okay, now similarly, due to the extraction of holes from N to P, there is a hole diffusion current along the quasi-neutral N region. And after extracted across into the P region, they become the majority carriers and they drift to give you a hole drift current. Now, the second red color assumption is important now. When the electrons and holes are extracted across the space charge region, no further generation of electrons and holes occur within the space charge region. And because of that, this current here is a constant. This electron extraction current is a constant. And this hole extraction current is a constant. All right, so since these are the only two currents flowing across the space charge region under reverse bias, the sum of the two currents will give me the total current flow under reverse bias condition. So the same two equations can be used to obtain the total current flow, and therefore the ideal diode equation that we derive for the forward bias case is also applicable to the reverse bias case. Okay, in fact, the assumption of forward bias during the earlier discussion was made just to facilitate the discussion. There is no need to make this assumption actually. Okay. All right, so that completes the whole picture. Now, the electron drift current has also two components. One is the constant component due to the extraction from the P side, and the distance dependent component is arising from the thermal generation process that happened within the quasi-neutral region. All right, the holes that are thermally generated will diffuse towards the edge of the space charge region for extraction to the N side, whereas the electrons that are thermally generated within the quasi-neutral N region will drift along in the opposite direction to give an electron drift current. Okay, all right. So with this, the whole discussion is complete now. All right, and we have finally achieved our aim of deriving the ideal diode equation that quantifies the amount of current flow under a given external voltage bias. Okay, now moving on, there's a name given to this constant J0. All right, it is commonly known as reverse saturation current density. It's useful to understand why people give it such a name. All right, this is how we can understand it. Now, assume reverse bias, right? Because of the word reverse, so it suggests that this name was adopted because of something happening under reverse bias. So let's consider reverse bias where VA is negative. Now, when the magnitude of the negative VA is much bigger than KT over Q, and keeping in mind that VA is negative, this exponential term will tend to 0. Meaning that under reverse bias condition, the current is actually a constant current determined by J0 or minus J0, denoting the direction of the current, right? Under reverse bias, the current flow in the opposite direction, so we have a minus J0 here. Okay, all right. So it's quite, therefore, quite intuitive to call this term J0 as the reverse saturation current density. because the current under reverse bias seems to be saturated at a fixed value, right? So J0 is called the reverse saturation current density. Now, to further understand why the current under reverse bias is constant and doesn't change with reverse bias, we can go back to this diagram here. Right. This is the plot for reverse bias. Remember, under reverse bias, we have minority carrier extraction, and therefore, the minimum value of the minority carrier concentration at the edge of the depletion region here is 0. It cannot go below 0. In other words, the concentration cannot be negative. So the minimum value of the of the electron concentration at the edge of the quasi-neutral region on the p side is 0. Similarly, the minimum value for the whole concentration at the edge of the depletion region here on the n side is 0. Now, with fixed doping concentration, Pn0 and Np0 are fixed. Essentially, under reverse bias, the concentration gradient in the minority carrier concentration is fixed. So when the reverse bias is large enough to make the minority carrier concentration at the depletion edges 0, the concentration gradient from then on is fixed. So any further increase in the reverse bias will not change the diffusion rate of the minority carriers across the quasi-neutral region, which supply the extraction of minority carrier across the space charged region. So since the diffusion is fixed, therefore the current flow under the reverse bias case is fixed, independent of VA when VA gets sufficiently large compared to KT over Q, right? Now, on the other hand, the current does not saturate under forward bias, all right? Because under forward bias, we have injection of majority carriers across the junction. And this injection gets more and more, right, as the forward bias is increased. All right, because holes are abundant here in the P region and electrons are abundant in the N region. With increase in the forward bias, the potential barrier is reduced, so many holes and many electrons can cross the junction. Right, so the current under forward bias does not saturate, but instead it increases exponentially with the applied voltage. Okay, so it's good to understand the physics behind the ideal diode equation. Okay, and you'll be able to appreciate. You'll be able to appreciate why people give certain terms certain names. Okay, all right. Take note that J0 depends on the dopant concentration, the carrier diffusivity, and lifetime through this expression here. And notice that it also depends on the temperature. Okay, because Pn0 and Np0, they themselves are a function of temperature and the band gap energy of the semiconductor through the intrinsic concentration term Ni. Because Np0 is Ni squared over Nd, and Np0, Pn0 is Ni squared over Nd, and Np0 is Ni squared over Na. So Ni squared term is actually inside this expression, which makes J0 dependent on the band gap of the semiconductor material. Okay. So with a larger band gap, if you build a PN junction using a semiconductor having a larger band gap, then J0 will be very small. And it's quite easy to relate back to the physics to understand why that is the case. Okay. All right. Some more comments on forward and reverse bias. Now, under forward bias, VA is positive and is typically much larger than KT over Q, at least 10 times or more to turn on the PN junction. The exponential term in the bracket is much greater than 1, and the 1 can therefore be neglected. And doing so allow us to linearize this equation by taking natural log on both sides. And you can see that this is a linear equation. If I plot natural log of J versus VA, you should get a straight line whose slope is Q over KT. Okay, now under reverse bias, I have I've already discussed this. So the current will become a constant minus J naught. Okay, so J naught is called the reverse saturation current or current density. Okay. Now this is for ideal diode. All right, so that will be the IV characteristic of the ideal diode, right? So under forward bias, the current rises exponentially with the applied voltage, and under reverse bias, it saturates at a certain fixed value, J naught. Minus J naught simply denotes the opposite flow of the current under reverse bias. All right, so this is a plot of natural log J versus VA. You should get a straight line whose slope is Q over KT, and by extrapolating the straight line to cut the y-axis or the natural log J-axis, you can determine the value of the J naught experimentally. If you can do an experiment like this, which is what you're going to do for lab 3. Okay, all right. Now, okay, ideal diode. All right, so at this point, we have an equation that describes the IV relationship of an ideal diode. But no diode in real life is ideal. Okay, the ideal diode comes about that give us such a simple equation for the IV relationship is simply because of some of the assumptions that we have made in deriving this equation. So a practical diode, strictly speaking, does not obey the ideal diode equation. It tends to deviate from the ideal diode equation. There are two main reasons for the deviation. In fact, three, right? The first reason is because in a practical diode, under forward bias, when carrier injection takes place across the space charge region, there is a non-zero recombination of electrons and holes in the space charge region, which is neglected in the derivation of the ideal diode equation. So the current under forward bias cannot be accurately described by the ideal diode equation because we neglect the recombination current that exists within the space charge region. Now, under reverse bias, a similar argument holds. Under reverse bias, remember in the earlier discussion on the ideal diode, we assume no generation of electrons and holes within the space charge region. But in fact, there is. There is a net generation of electrons and holes within the space charge region. So in other words, the current under reverse bias condition is also higher than what the ideal diode equation predicts. Okay, so the ideal diode equation is strictly not valid. I mean, not strictly valid for a practical diode. But to analyze a practical diode right from scratch is a very challenging problem because of all the difficulty related to the effects that I just mentioned, like the recombination of electron and holes in the space charge region and the generation. So if we account for all this, there is no analytical solution possible. Okay, so in order to still make use of the ideal diode equation to describe the IV equation of a practical diode, what people have done is that they introduce an additional parameter, N, into the ideal diode equation. Now, N is introduced at this position here, right? It's at the denominator of the exponent here. Now, N is called the ideality factor. All right, why people call N the ideality factor? Now, when N is 1, this equation goes back to the ideal diode equation. All right. Now, when N is not 1, greater than 1, then of course this equation is no longer the ideal diode equation. And typically for a practical diode, if we try to fit the IV data to this equation, we will get a value of N that is greater than 1. Usually N is between 1, greater than 1, but less than 2. All right, it's between 1 and 2. Okay, and the ideality factor can be determined in the same way as what I mentioned earlier by plotting natural log J versus VA. All right, the slope of this straight line will allow you to determine N, the identity factor. So this is what people normally do after a diode is being fabricated. They will measure the IV curve, right, and then try to determine the identity factor. If the identity factor is close to 1, like 1.1 or 1.2, then the diode is relatively ideal, right? And if it deviates too much, then there are some non-ideal effects that are taking place inside the PN junction. Okay, all right. So in lab 3, you will learn how to determine the non-ideality factor of a practical diode, practical PN junction. Okay. Now let's look at some examples, and then we should be able to close for the day. So let's calculate some parameters and have a good feel of the order of magnitude of some of the parameters. So let's determine the reverse saturation current density of an ideal silicon PN junction with the following parameters. All right, so the doping concentrations are given, the diffusivity of holes and electrons, and as well as their respective light times in the quasi-neutral region. Okay, right. So to do that calculation is quite simple, right? So all you need to do is just to determine LP, all right? Instead of calculating LP explicitly, we can re-express this in this form by noting that the definition of L, right? The minority carrier diffusion at LP or Ln. So I only write L here for in general, right? So L square is D times tau. So I can manipulate this such that D over L can be written as L over tau, which can then be expressed as square root of D over tau. So in other words, dP over LP can be replaced by square root of dP over tau p, and dN over Ln by square root of dN over tau n. All right, so instead of calculating LP or Ln separately, you can directly calculate J naught if you can realize this. Okay, so putting in the numbers, you can obtain J naught to be 4.15 times 10 to the power minus 11 ampere per cm squared. Per cm squared. Cm squared is a very big area for a PN junction. Normally, the cross-sectional area of a PN junction is very small, right? And therefore, the actual reverse bias current that flows is actually much smaller than this. And not surprising because the current flow involves extraction of minority carriers, which they themselves have very low concentration. Okay, all right. So let's look at the second example. Consider a silicon PN junction diode at 300K. Design the diode such that Jn is 20 ampere per cm square and Jp is 0.2 ampere per cm square. Now, these two currents refer to the minority carrier diffusion current at the depletion edges. Okay, all right. Now, as you know, by adding the two, we get a total diode current. Okay. So you're asked to determine the doping concentration of the diode such that we have Jn as this value and Jp as this value. Okay. So you need to go back and look at the expression for Jn. Now, since I said that this current refers to the value of the current at the edge of the depletion region, in other words, x double prime is 0. So the exponential term is not in this expression, it's actually a 1 here. All right, so with this, we can rearrange it such that the only unknown in this equation is actually Na, such that Na can be solved. Okay, all right. So we can design the diode by doping the P side to this value. And then we can also determine Nd based on the other value for Jp. And then from there, we can also find Nd. So if we dope the P and N regions, right, in this way, we can literally control, right, the amount of current that flows under the forward bias condition. So you can design diode having different forward bias current by manipulating the doping concentration of the P and N region. Okay, all right. Yep, that's the point that I want to make. Now, notice that if we dope a diode such that one side of the diode is more heavily doped than the other, the current will be dominated by the injection of carriers from the heavily doped region to the more lowly doped region. Okay, in fact, this can be seen from the above example. Since ND is bigger than NA, the JN is bigger than JP, right? So the current, the total diode current is mainly made out of the electron diffusion current in the lowly doped P region. You can double check. So ND is 10 to the power 16, 6 times 3, 9 times 10 to the power 16. And NA is only 10 to the power 15. So they are more than 10 times difference. So the whole concentration is 10 times lower than the electron concentration in the N side. All right, the whole concentration on the P side is 10 times lower. So under a given forward bias voltage, electron injection dominates. Right, more electrons are injecting from the N side to the P side, and therefore the electron diffusion current in the quasi-neutral P region is higher than that of the host. In this example, okay. Now to take this further, you can assume that if you dope the current, if you dope the PN junction more heavily on one side compared to the other side, the total diode current is actually made up of the diffusion current arising from the injection of minority carriers from the heavily doped side. And that makes a lot of sense, all right? Okay. Yeah, so with this, I think we can finish the class today. Now, before I leave, I just want you to think a bit more about this question. So consider an abrupt uniformly doped silicon PN junction subjected to a given forward bias voltage. If one wants to increase Jn, in other words, Jn refers to the electron diffusion current in the quasi-neutral P region arising from electron injection from the N side. Okay, so which doping concentration should we change? Assuming the rest of the parameters are not to be changed. So if I want to increase Jn, so which doping should you change? Okay, you can think about it and we can discuss next time in the next class. Right, so I want you to think a bit more about this. Okay, so we are done for the day.